Hi all. So as a continuation of relational algebra operations, now we'll be seeing about the set operations. So relational algebra operations from set theory. So the possible operations that you can perform on a relational algebra is union, intersection, set difference. Set difference is also known as minus or exit. So now let's start with an example. Here the query is to retrieve the SSN number, that's a social security number of all employees who either work in department 5 or directly supervise an employee who works in department 5. Okay, so here we are trying to use union operation. So let's see the steps for writing a relational algebra expression for the given example. So the first part of the example is asking to retrieve the employee who work for department number 5. So the initial step here we can see that's a select operation. So select employees from department number 5. Okay, so that is intermediate result is saved in the relation dep5 underscore emps. Okay, now after that we have to select the social security number, only the social security number, that is the attribute that we need, right? So for that we will be using the project operation. So project operation here you will be performing on the result of the first step, that is to select the employees in department number 5. So department number 5 underscore EMPS is fed in as an input to project operation, whereas this project operation is going to select only the SSN number. Okay, so with that, in the result one, this intermediate result, in the result one we have the SSN number of all the employees who work for department number 5. Next part of the query is who are going to supervise the supervise department 5, right? So that is a super SSN attribute which gives the supervisors list. Okay, so now dep5 underscore emps. So here in this we have all the employees who work in department number 5. So the employee, one of the attribute is who is a supervisor for that particular employee. So pi, that is a select project operation, right? It will return only the attribute super SSN, and that is saved in the result 2. Okay, and it is renamed, the attribute is renamed as SSN. Okay, now in result 1 you have the list of all the employees who work for department number 5, and in the result 2 you can get the who are the direct supervisors uh, an employee who works in department number 5. Now if you combine this, that's a union. The original result is a union of these two results. Okay, so they are the steps and this is explained here. The next slide we can see in detail how this is executed, right? As a single relational algebra expression, now this is a intermediate results, right? So we have broken the whole query into multiple steps, and or we can write it as a single relational algebra expression as this. Okay, so this is equivalent to this. It is your wish to if you want to write it as a single relational algebra expression, or you can combine it with intermediate steps. So these are the steps that we discuss. So this is your original employee table. Okay, you can see the attribute f name, m init, l name, ssn, b date, address, sex, salary, super ssn, d number. Right now, this employee attribute, right? This is the result of your first selection, right? That is, select all the employee who work for department number 5. right? So you got 4 employees who work for department number 5. From that, so you will get the result 1. What is result 1? Result 1 is you have to extract, that is the projection of SSN. So you will get this column, right? This column of the employee. So employee who works in department number 5. Next, union, right? What is this result? Result 2 is a projection of super SSN. Super SSN, you can see there are 4 tuples, right? Of which only 2 are unique or distinct. So you will get the employee who works, sorry, here you can see a typo, the employee who supervises the particular employee, okay? And the result is a union of these two. So you will get the result of union operation after duplicate removal as this, okay? So this is how the union operation is performed on a relation. Next, the union, intersection and difference, they have the usual meaning of what the operations are performed in the set theory, right? So now instead of a set theory or set, here we are going to apply the union, intersection, difference operations on a relation, okay? The relation is nothing but a set. The result of this operation denoted by R union S, right? And it is a relation that includes all tuples that are either in R or in S or both R and S, okay? So duplicate tuples are eliminated. Intersection is also having the same meaning as the set theory notation, and set difference or minus, that is, it is represented by R minus S, is a relation that includes all tuples in R that are, all tuples that are in R but not in S. Okay, we can see these operations with examples. Now, in order to perform all these operations, we need to be compatible. The two tuples or the two relations involved in this operation, set operations, need to be compatible to each other. Now, we'll see what is meant by union compatible. Okay, so the two relations on which any of these three operations are applied must be of the same type of tuples, right? So this condition is called as union compatible. So here you can see two relations. One is R and another one is S, and each of them are performed, the attributes are A1, A2, etc. up to AN, and in set S or in relation S you have attributes B1, B2, etc. Bn. So when can you tell that this is an union compatible or type compatible? If they have same degree, that is number of attributes in both R and S should be same, and if domain of A is equal to domain of B for all attributes, then we can say that it is union compatible. By domain, you mean the data type or the domain constraint, right? So that's a condition for union compatible. So what are the two conditions? First one is the degree of two relations which are involved in any set operations should be same, and all the attributes in both the relations should be domain compatible, right? That is, domain of A is equal to domain of B, like that for all A's, and for all B's the domains should be matching. Okay, so this means that two relations have the same number of attributes and each corresponding pair of attributes has the same domain. So once this compatibility is satisfied, then only we can apply the set operations. So now we'll see examples of each of these operations, that is union, intersection and difference. Here the two inputs are, you will have a student and instructor. So here the operation I need to perform is student union instructor. So what is the output here is, you can see all the tuples, right, without any repetition, right? So that is the answer. You can just check it It's just a union of these two sets. If they are repeating, they are included only once. Union here is the next example. You have a graduates table and managers table. Union is graduates union manager. So you can see here 7274, 7432, 9824 and 9297. 9824 is repeated twice, but in union the duplicates are not allowed and it is collapsed to one entry. Intersection, the next operation, you can see the elements or the tuples that are common in both the entries or both the relation, that will be the output. So here you can see Susan Yao and Ramesh Shah are the common. That means they have the both the roles as a student as well as an instructor. Next example, graduates, you can see 7432, 9824. They are common in both the tables, right, or both the relations. So that will be the output of intersection. Set difference is the next operation. So in the next operation you can see student minus instructor. That means all the elements in student but not in instructor. So you can see Susan Yao, but Susan Yao is present here in instructor. So we can't include that as an answer. Ramesh Shah is also present in instructor. Rest all are not member of instructors, right? So you will get the list of students. Okay, now next operation is instructor minus student. So who are all the instructors who have the role of instructors only, right? So John Smith, then Ricardo Browning and Francis Johnson. So uh, these three tuples or records are the instructors. Another example here is graduates managers. So graduates minus managers, you can see only one tuple. So they are the operations. Now we'll see the properties of the set operations. So union, intersection are commutative operations. You can see R union S equal to S union R and R intersection S is equal to S intersection R. Both union and intersection can be treated as n-ary operation, right, applicable to any number of relations because both are also associative operations, right? So you can connect this union with n number of relations, right? So it becomes n-ary operations, and all the operations or all the operations are associative, right? So that's a property. Next, and the minus operation is not commutative. That is, in general, R minus S is not equal to S minus R, which we have seen from this example, right? Student minus instructor is different from instructor minus student. So set difference is not commutative. Now, a different example where we use renaming just to make it common, right? Because in order to have a compatibility. So here you have maternity table and paternity table, right? So you have mother child and father child. But is there a logic of paternity union maternity? So what we will be doing is first we will rename the table, right? So renaming using row operator, maternity table is renamed, the attribute is renamed as parent child, and paternity also it is made as parent child. Then you will can perform an union of both the tables by making it parent child, right? So this is a compound expression. Here you can see the left hand side of union is a maternity table where the attribute mother was renamed to parent, and for the paternity table the attribute father was renamed to parent, and the union operation is performed on the resultant renamed operation. So you will get this as a table. Next, renaming and union with several attributes, right? So more than one attributes we are trying to rename. right? So you have employees, you have surname, branch, salary. Then you have staff, surname, factory, wages. So here we are renaming. Here you can see the employees table is renamed. The attribute is renamed as surname, location, pay of employees. And here you can see the row of, that is the row operator is for renaming surname, location, pay of staff. Now if you can perform an union, you will get this as a table. Now we can see an example, right? So you can also try it parallelly. How can we find answer or relational algebra equivalent for this query? So what is the query here is to find all course IDs taught in the fall 2009 semester or in the spring 2010 semester or in both. Okay, so what does this mean is actually an union operation, right? In both or in 2009 or in 2010, right? So we have to do an union operation. Now let us assume that the schema on which you have to perform this query is section. The relation name is section and it has attributes course ID, course name, semester, year, program, branch. Now what you have to find is courses taught in fall 2009 and courses taught in spring 2010, right? So you have to do the union operation of this. Now we have to further dissect these into relational algebra expressions. So you can see here sigma, right? Why sigma? You are going to select the courses that satisfies this condition. What is a condition? The semester is fall and the year is 2009, right? So of this you are getting uh, all the courses that are offered in fall of the semester and the 2009 and in the year 2009. Similarly here semester is spring and year is 2010. Okay, hope this is clear up to this. Now we got the left hand side is, you can see, you will get the all the courses which was offered in uh, 2009 fall, and in the right side you can see all the courses that offered in 2010 spring. Next what we have to do is we need only the course ID, right? What attribute we need at last is only the course ID. So now what you have to do, you have to do a project operation on the answer, right? So what is output you are expecting is course ID. So pi of course ID. Similarly here also pi of course ID to this. So now you got two results, that is course IDs of the courses that are offered in fall 2009, and this side you will get the course IDs which is offered in fall 2010. Now if you do an union operation, you will get the corresponding relational algebra expressions for the given question, right? So this is how you can frame a relational algebra expression. Next question, one more example here is to find all courses taught in fall 2009 semester but not in spring 2010 semester. That means a set difference, right? So instead of union, right, as the above example, instead of union you would be doing a set difference. Okay, so that's how the set theory a set operations are performed on the relational algebra operation. So let's summarize. Here one of the three operations that you can do are union, intersection, set difference, and each of these operations which are involved in the set difference should be type compatible or union compatible. Type compatible means what? The date type compatible or union compatible, which means the degree of the relation or the degree of the relation which are involved in the set operations should be same, and each of the attribute in the relation should have the same domain. Okay, so if that compatibility is satisfied, only then you can perform the set operations. And we have seen the examples for each of the operations. Thank you.